So we've been looking at how to simplify expressions. We can now bring all of this together in combinational logic. Combinational logic circuits are those that have no memory. So it's simply these gates that we put together to provide a certain function. So you learn how to design circuits which have more than two levels of AND and OR. And then in the second part, we'll look at how to use the NAND and NOR gates. So we'll learn the design of a minimal two-level or multi-level circuits of AND and OR gates. We'll design or analyze a two-level gate using any one of the 8 combinations. We would convert circuits of AND and OR gates to circuits of NAND gates or NOR gates. So, and then design minimal two-level multiple outputs AND or OR gates. There are a number of 5 key things that you need to know. How to develop NAND circuits from K-maps. There are two-level implementation, a multi-level NAND gates, exclusive OR, and then parity checking. Those are the key things that you need to know or learn. The recommended text is chapter 7 of your book, Fundamentals of Logic Design. There are a few terms that you may have to or you need to know before you can proceed, right? And these are AND OR circuit means a two-level circuit composed of a level of AND gates followed by an OR gate at the output. An OR AND circuit means a two-level circuit composed of a level of OR gates followed by an AND gate. OR AND OR circuit means a three-level circuit composed of a level of OR gates followed by AND gates and followed by an AND gate. A circuit of AND and OR gates implies no particular ordering of the gates. The output gate may either be AND or OR. The number of levels in an AND/OR circuit can usually be increased by factoring the sum of the products from which it was derived. Similarly, the number of levels in an OR AND circuit can usually be increased by multiplying out some of the terms in the product of some expressions from which it was derived. So let's look at the implementation of two-level logic. Yeah. So in a two-level logic, you have a sum of products, AND gates to form a product terms, mean terms, or OR gates to form the sum. So you have something like that. So the AND gates, which are then combined to form into an OR gate. Yeah. Or for the sum of products, and then the product of sums where you have OR gates and OR gates combined into an AND gate. So these are two-level logic. Now you can represent two-level logic using NAND gates. You know, a NAND gate, you know, is an AND gate that has got an inventor at the end. So you replace the mean term AND gates with NAND gates and place compensating inversion at the outputs, you know. So you replace what? The AND gates with NAND gates, yeah, and a compensating inversion at the outputs. So these ones you replace with that. So this is what you have. Such a circuit, a typical will look something like that. So you have that circuit that goes to become this, right, with an inverter at the end now, and then this one then you replace with a NAND gate, another NAND gate. So once you do this inversion, then the signal division is also done, and that is it. So the OR gate with inverted inputs is a NAND gate. So an OR gate with an inverted input is an OR gate, and that you can verify that using De Morgan's rule, right? Now we can look at that as at this thing. Let's say a function A, B, or C, and D or E or F and G or an H. So this will have different levels. So you have your A and B here, F and G there. Then the next level, you OR the output of A and B with a C, and then you OR the output of what? D and E with the output of F, G, and then you then end the output of the level 3, and finally you OR that at the final stage. So you can see the way in which it's done, level by level, step by step. So you can attempt then to write out the logic function for this whole thing here. Again, step by step, you can go there and verify this for yourself. Of course, you can use the same gate. Once it appears, you can use it again and again. Once it doesn't contravene anything, you can use it over again. So, for example, there's a DE here, and the same DE here, which is appearing. So you can use the same gate, for it, because it's the same DE, that is appearing. So you don't have to make another one. You see that DE there? The output you can use in both places. So you don't have to draw another DE. So it means you can simply tap the signal, and distribute it. Now, we have a certain function, and then we want to find a circuit of AND and OR gates that will realize this function. This function of A, B, C, and D is given by the min term 1, 5, 6, 10, 13, and 14. This means that we need to do the Kano map, put these things there, and then attempt then to minimize that. So the function then given A, 1, 2, 3, 4, 5, 6 for the ends, and then the ORs we use the zeros, right? So for the function, for the ends, this is what you get. For the two-level OR gate, you need 5 gates, and this is what will give you that. The function you see earlier here would lead to something of this nature. So you have 2 level 5 gates, 16 gate inputs. That again is developed further here, 3 level 5 gates for the other one, which you can work through step by step to see how this evolves. Here, another example of it again is the 2 level 5 gates, 14 inputs for the same function. Now, how do you use the NAND and NOR gates? So you have a 3-input NAND gate, which basically is an AND gate, which is then negated. A NAND gate is simply an AND gate with a negation at the end. So the symbolic representation of that is one symbol like this. Of course, you can have an N-input NAND gate, where you have several inputs, and then you then negate it. Now, using De Morgan's rules, you can write this function, for example, as not A, or not B, or not C. So basically, this function here, which is what? A and B and C all negated, can be written simply as not A, or not B, or not C. Now, further the NOR gate, again, you can think of it in terms of what? An OR gate, which is then invented. So you have 3 inputs, and then you invent the output. Of course, you can have a multiple input NOR gate as well, with several inputs. Now, if you look at that carefully, this means that the function actually being defined here is F, A, or B, or C, all of that negated, right? Using Boolean algebra, that actually results in not A, and not B, and not C. That's what it stands for. So that's sort of, simplifies or tells you what NAND gates and NOR gates are, right? Look again in the test, and you find further details about this for you to read and understand. Now, a set of logic operations is said to be functionally complete if any Boolean function can be expressed in terms of this set of operations. The set AND, OR, and NOT obviously is functionally complete because any function you can represent it, in this way as a sum of products or the product of sums. In a similar way, a set of logic gates will be functionally complete if all switching functions can be realized using this set of gates. Because a set of operations AND and OR and NOT is functionally complete, any set of logic gates which can realize AND, OR, and NOT is also what? Functionally complete. So NAND gates, right? If you have a single input X, right, you can combine that and make two X's, and then the output be a NOT X. Same way, you can have A and a B. That gives you what? NOT AB. Now, if you input that here, then that gives you AB, which means that the NAND gate realization of NOT, so it means you can use a NAND gate to realize a NOT and an AND and an OR. So the NAND gate can be used to realize just all the other functions, right? So in this case, we are using the NAND gate to realize what? A NOT. Yeah? So you have X, you want to take a NOT X, you just double that input into it and you get a NOT X. And then you can use the same thing to realize, you get a NAND, which gives you this thing, an A not B, an A not B now, which you can then use to get the inverse of it, which is AB. Right? Now, how do you use the NAND gates to realize an OR function? This shows you how you can use a NAND gate to realize an OR function. So look at that. You get the A input here, the B input there, right? So the A input here, as from here, begins NOT A, as in this case gives you a NOT B. The NOT A, NOT B, you end that, which gives you not AB, which is A and B, or B. So you've realized what? A or B using what? Simply NAND gates. The same way you can use a NOR gates to realize any of these functions, right? So how to conversion using the NAND gates, you should find a minimum sum of products expressions for them. Draw the corresponding two-level AND OR circuit. Replace all gates with NAND gates, leaving the gate interconnections unchanged. And if the output gate has any single literal as input, complement this literal. So this gives you what? A procedure for designing a minimum two-level NAND circuit. We can do the same thing. So that's an example before the transformation. This is what you have, and this is what you get after the transformations. You can do a similar thing for the NOR gate, a similar procedure for the NOR gate. So remember, the key thing here is that you can use a NAND gate to represent practically all, not practically, all NOT gates, AND gates, or OR gates. So this is what we are saying. And the same way, you can use a NOR gate to represent the same things. So they are what? Logically complete. Now, something for you to consider, a question for you to consider. Using AND and OR gates and a minimum circuit to realize these functions, use a two-level logic and use three-level logic. That's 12 gate inputs. Attempt that and see what you get. Thank you.